Welcome back, students. Today, we're delving into the intriguing world of molecular shapes and their connection to function. Just like orchid flowers showcase how their shapes serve a specific purpose, molecules also adopt distinct shapes that are closely tied to their functions. Take, for instance, the fascinating example of the bee orchid. This orchid species, scientifically known as Ophrys epiphyra, boasts a central labellum that astonishingly resembles the abdomen of a bee. Not only that, but the labellum is even slightly hairy, adding to its mimicry. The orchid emits a scent reminiscent of a female bee, further enhancing the illusion. The purpose behind this mimicry? Pollination. When a male bee attempts to mate with the orchid, pollen gets transferred onto the bee, only to be unwittingly carried to another bee orchid, achieving the crucial task of pollination. So, just as the bee orchid's shape influences its function in the natural world, molecular shapes play a vital role in the behaviors and interactions of molecules. Fascinating, isn't it? Let's continue exploring. Good day, students. Today's chapter takes us deep into the world of molecular structures and their connection to Lewis structures. Our journey starts by unraveling the fascinating relationship between two-dimensional Lewis diagrams and the three-dimensional shapes that molecules adopt. It might surprise you to know that the number of electrons within a molecule plays a crucial role in determining its overall shape. Armed with this knowledge, we can delve further into the nature of covalent bonds, those bonds that hold atoms together within molecules. But how do we decipher the clues hidden within Lewis structures? The lines used to represent bonds in these structures provide us with important insights into the orbitals that molecules utilize when forming bonds. Through a closer examination of these orbitals, we can unlock a deeper understanding of how molecules behave and interact. So, let's embark on this exciting journey of discovering the secrets behind molecular shapes and the intricate world of covalent bonding. Good day, students. Today's lesson is a fascinating journey into the world of molecular geometries. By the end of this section, you'll be equipped with the knowledge to recognize the fundamental shapes that ABN molecules can take. Now, as we venture deeper into this topic, remember that while Lewis structures provide us with valuable information about the bonding in covalent compounds, they fall short in revealing the actual shapes of molecules. For instance, let's consider the Lewis structure of carbon tetrachloride, CCl4. We can see the 4 chlorine atoms bonded to a central carbon atom. However, this structure doesn't give us insights into the spatial arrangement of these atoms. Let's proceed to unravel the mysteries of molecular geometries. Hello again, eager learners. As we delve deeper into molecular geometries, it's crucial to grasp the limitations of Lewis structures. While they offer information about the bonds within a molecule, they don't provide insights into the three-dimensional arrangement of atoms. Take the example of carbon tetrachloride, CCl4, we discussed earlier. The Lewis structure beautifully demonstrates the bonding between the carbon and chlorine atoms, but it doesn't clue us in on how these atoms are positioned in space. To fully comprehend the behavior and properties of molecules, understanding their shapes is of paramount importance. Let's proceed to uncover the key concepts that will help us determine these shapes. Welcome to a pivotal part of our discussion, my attentive students. We're now ready to connect the dots between molecular shapes and Lewis structures. Our focus will be on molecules of the type ABN, where A represents the central atom and B represents the surrounding atoms. These molecules come in various geometries, and understanding the relationship between their shapes and Lewis structures is a key piece of the puzzle. We'll also introduce the concept of valence electron pairs, which plays a crucial role in determining these shapes. Picture in your mind molecules like AB3 and AB2, where the arrangement of atoms is influenced by the number of valence electron pairs. Let's continue our exploration. Greetings, curious minds. Here's where the excitement escalates. We're about to dive into the heart of molecular geometry by exploring the 5 fundamental shapes that ABN molecules can adopt. These shapes are the building blocks of molecular arrangements, and they are tetrahedral, trigonal planar, linear, trigonal bipyramidal, and octahedral. Each of these shapes has distinct characteristics that stem from the arrangement of valence electron pairs around the central atom. From the tetrahedral shape resembling a pyramid to the linear shape that extends in a straight line, we'll uncover the unique qualities of each. So, let's embark on this enlightening journey into the world of molecular shapes. Hello again, inquisitive scholars. Let's begin our exploration of the 5 basic molecular shapes with the tetrahedral geometry. In a tetrahedral shape, the central atom is surrounded by 4 bonding pairs of electrons, creating a pyramid-like structure. Molecules like methane beautifully exhibit this shape. Notice how the bond angles between atoms contribute to the overall 3-dimensional arrangement. Keep in mind that the specific angles and arrangement of atoms play a significant role in the properties and behavior of these molecules. Let's continue our journey by uncovering more about this fascinating molecular configuration. Hello there, dear students. Today, we're diving into the captivating world of molecular structures and their true 3-dimensional arrangements. Our journey starts with something you might be familiar with, the Lewis structure. This is a simplified representation of molecules where all the atoms are drawn in the same plane. However, as we'll soon discover, reality often has more surprises in store for us. Take a look at Figure 9.1, where we see an example of a molecule's Lewis structure. In this case, we have chlorine, Cl, atoms involved. Now, brace yourselves for the twist. The actual arrangement of these atoms in 3-dimensional space is quite different. Imagine the chlorine atoms at the corners of a geometric figure called a tetrahedron. This tetrahedron has 4 corners and each face is an equilateral triangle. So, what we initially thought was a flat picture turns out to be a 3-dimensional marvel. This is a great reminder that sometimes our simplified models don't capture the full complexity of the world around us. Now, let's journey further into the fascinating world of molecular geometry. Hello, students. Today, we're stepping into the fascinating realm of molecular shapes. Our journey begins with molecules that have a distinctive structure, a single central atom bonded to 2 or more atoms of the same type. We use the general formula ABN to describe these molecules, where the central atom forms bonds with n atoms of type B. To put this into perspective, let's look at some examples. Both CO2 and H2O are categorized as AB2 molecules. In CO2, one central carbon atom is bonded to 2 oxygen atoms. Similarly, in H2O, a central oxygen atom is bonded to 2 hydrogen atoms. Moving on, we have AB3 molecules like SO3 and NH3. In SO3, a central sulfur atom is connected to 3 oxygen atoms, while NH3 features a central nitrogen atom bonded to 3 hydrogen atoms. This pattern continues as we explore more complex molecular shapes. Now, let's delve deeper into the intricacies of these molecular structures. Good day, students. In our lesson today, we're going to delve into the intriguing world of molecular shapes, particularly those of ABN molecules. These shapes depend on the value of n, which we'll explore further. Let's begin with AB2 molecules. These molecules can have 2 common shapes: linear, where the bond angle is 180 degrees, and bent, where the bond angle isn't 180 degrees. Imagine the structural implications these variations bring to the molecules. Moving on to AB3 molecules, we encounter even more fascinating shapes. The primary shapes involve placing the B atoms at the corners of an equilateral triangle. If the A atom is in the same plane as the B atoms, we have a trigonal planar shape. But if the A atom is positioned above the plane of the B atoms, we get a trigonal pyramidal shape. Visualize a pyramid with an equilateral triangle base. Now, here's where it gets interesting. Some AB3 molecules, like ClF3, adopt a T-shaped configuration. This is quite an unusual shape, and it's characterized by the atoms lying in a single plane with 2 BAB angles at around 90 degrees and a third angle close to 180 degrees. The intricate world of molecular shapes offers us insights into the arrangement and interactions of atoms within these compounds. Let's proceed to the next topic to explore more. Good day, students. Today, we're delving into the intriguing world of molecular geometries, where we'll uncover the fascinating arrangements of atoms within ABN molecules. Our journey begins with the realization that most ABN molecules can be understood through just 5 fundamental geometric configurations. These arrangements exhibit remarkable symmetry, and they all involve the distribution of Nb atoms around a central atom. Now, let's proceed to explore these intriguing shapes. Alright, students, let's start with the first basic geometric arrangement, the linear configuration. In this setup, we have 2 atoms, A and B, positioned in a straight line. The bond angle between them measures a perfect 180 degrees. You can imagine this as if they're forming a line segment. Examples of molecules with linear geometry include those where an atom A is bonded to just 2 atoms B. This straightforward arrangement sets the stage for our exploration into more complex shapes. Now, let's move on to the second geometric arrangement, the trigonal planar configuration. Here, we find 3 atoms, A and 2 B atoms, arranged in a flat plane. The bond angles between these atoms are consistent at 120 degrees each. Visualize this as a triangle on a plane surface. Numerous molecules adopt this trigonal planar geometry when atom A is bonded to 3 atoms B. This is a common arrangement that we've already encountered in our journey through molecular shapes. Moving forward, let's explore the third fundamental geometry, the tetrahedral configuration. This arrangement involves 4 atoms, A and 3 B atoms, coming together to form a pyramid-like structure. The bond angles within this shape are around 109.5 degrees each. Think of it as a 3-sided pyramid with the apex pointing upwards. Whenever atom A is bonded to 4 atoms B, this tetrahedral geometry often emerges. It's a key arrangement with implications in various molecular contexts. Hello, dear students. Today, we're delving into the intriguing realm of molecular shapes and the remarkable valence shell electron pair repulsion, or VSEPR, model. You might be wondering why most ABN molecules have shapes that resemble the ones depicted in Figure 9.3. Well, worry not, because we're about to unravel this mystery. When it comes to answering questions about molecular shapes and predictability, especially for elements from the S and P blocks of the periodic table, the VSEPR model is our trusty guide. Despite its complex-sounding name, this model is surprisingly simple and incredibly powerful in predicting molecular shapes. In fact, its predictive prowess will shine through in section 9.2 as we delve deeper. So, buckle up and let's embark on this enlightening journey. Welcome, students. Today, we're delving into the fascinating realm of predicting the shapes of molecules using the VSEPR model. You're about to learn how molecules arrange themselves in space, and it's a bit like tying balloons together. Imagine tying 2 identical balloons at their ends, just like in Figure 9.5. These balloons naturally orient themselves to stay away from each other. It's like they're trying to get out of each other's way. Now, let's explore what happens when we add more balloons. Fantastic! In the case of 2 balloons, as we saw in Figure 9.5, they naturally orient themselves to point away from each other. This phenomenon mirrors what happens with electron pairs in molecules. When molecules have valence electron pairs, these pairs repel each other to find a stable arrangement. The VSEPR model helps us predict this molecular geometry. Now, let's take it a step further. Isn't this intriguing? When we add a third balloon to the mix, something interesting happens. The balloons now orient themselves towards the vertices of an equilateral triangle. This concept directly relates to molecular geometry and chemistry. It's like we're witnessing the birth of trigonal planar geometry right before our eyes. Keep this in mind as we venture deeper. Brilliant observation. Now, let's take the balloon analogy one step further. When we add a fourth balloon, they adopt a tetrahedral shape, a pyramid-like arrangement. This directly corresponds to the molecular geometry of tetrahedral molecules. The VSEPR model helps us predict such intricate shapes. So far, we've seen that there's an optimum geometry for each number of balloons or valence electron pairs. This understanding is crucial as we dive deeper into molecular shapes. Welcome back, dear students. Today, we're delving into the fascinating behavior of electrons within molecules, and you'll be amazed by how similar their behavior is to something as simple as balloons. Just as balloons occupy space, a covalent bond is formed between two atoms when a pair of electrons occupies the region between them. This pair of electrons is called a bonding pair and defines what we call an electron domain. This domain represents the area where the electrons are most likely to be found. Now, remember that not all electrons are involved in bonding. We discussed this earlier when we learned about non-bonding pairs or lone pairs of electrons. These also create electron domains, but they're primarily located around a single atom. Let's take the example of ammonia, NH3. It has 4 electron domains around its central nitrogen atom. 3 are bonding pairs represented as short lines, and 1 is a non-bonding pair represented by dots. This arrangement of electron domains shapes the molecule's properties. So, whether it's bonding pairs or lone pairs, these electron domains play a pivotal role in determining a molecule's behavior. Let's move forward to explore more about this intriguing electron behavior and its impact on the world of chemistry. Hello, dear students. In our quest to unravel the mysteries of chemistry, we've now arrived at the intriguing concept of resonance structures and electron domains. Don't be alarmed by the terminology, we'll break it down step by step. Imagine molecules with multiple bonds. Each of these bonds is actually considered a single electron domain. Let's delve into a concrete example with ozone or ozone. In one of its resonance structures, ozone features 3 electron domains encircling the central oxygen atom. These domains include a single bond, a double bond, and a non-bonding pair of electrons. These electron domains significantly influence the molecule's behavior and reactivity. As we journey further, you'll see how these structural intricacies play a vital role in shaping the properties of different compounds. Welcome back, students. Today, we're delving into the world of electron domains within molecules. Let's begin by understanding that each non-bonding pair, single bond, or multiple bond contributes to the formation of a single electron domain around the central atom. These electron domains play a crucial role in determining the overall geometry and properties of molecules. Now, let's explore further. Hello, students. Today's lesson is getting even more intriguing as we discuss the relationship between electron domains and molecular geometry. You see, the number of electron domains around the central atom greatly influences how the atoms arrange themselves in a molecule. This, in turn, gives rise to various molecular shapes. We're talking about shapes like linear, trigonal planar, tetrahedral, and many more. So, remember, the arrangement of electron domains paints a vivid picture of a molecule's structure. Null. Hello again, students. Let's dig even deeper into the concept of electron domains. Think of them as regions of electron density encircling a central atom. Why is this important, you ask? Well, electron domains significantly impact the properties and behaviors of molecules. One crucial aspect they influence is bond angles. The arrangement of these domains shapes how atoms are connected within a molecule. As we uncover more about electron domains, we're uncovering the secrets behind molecular structures. Welcome back to our captivating journey, students. Here's an exciting twist. Electron domains also have a say in a molecule's polarity. When electron domains are distributed unevenly, we get polar molecules. These molecules have distinct positive and negative poles due to the asymmetry in electron distribution. On the other hand, even distribution of electron domains results in nonpolar molecules. So, you see, electron domains not only shape the geometry but also impact the overall nature of the molecules we encounter. null. Hello again, dear students. Today, we're delving into the fascinating world of molecular geometry and the VSEPR model. But what's this model all about? Well, imagine electron domains as tiny balloons filled with negative charge. They're not too fond of each other, much like how balloons in a crowded room would avoid bumping into one another. Similarly, electron domains strive to stay out of each other's way due to their negative charges. This brings us to the VSEPR model, which stands for valence shell electron pair repulsion model. This model helps us predict the three-dimensional shape of molecules by considering the repulsion between these negatively charged electron domains. As we move forward, you'll see how this model aids us in understanding molecular structures in a whole new light. Welcome back, students. Today, we're going to dive deeper into the analogy of electron domains being like balloons in a crowded room. Just as balloons filled with air repel each other to maintain some distance. Electron domains, loaded with negative charge, repel each other as well. This repulsion is crucial because it minimizes the potential energy of the system. Remember, in the world of molecules, nature strives to find the most stable arrangement. Much like balloons naturally settle into positions that avoid contact. Now, let's connect this analogy to the VSEPR model and see how it helps us decipher the shapes of molecules. Great to see you engaged, students. Now, let's bridge the gap between electron domain geometry and molecular shape. The number of electron domains around a central atom dictates the overall geometry of the molecule. Whether it's 2, 3, 4, or more, each arrangement results in a specific molecular shape. For instance, when we have 2 electron domains, they'll be farthest apart, leading to a linear molecular shape. With 3 domains, we move into trigonal planar and pyramidal shapes, depending on whether there are lone pairs involved. 4 electron domains give rise to tetrahedral and square planar shapes. It's truly a dynamic puzzle where both lone pairs and bonded pairs influence the final geometry. This understanding forms the cornerstone of the VSEPR model, helping us uncover the mysteries of molecular architecture. Hello again, inquisitive minds. Let's explore the real-world applications of the VSEPR model. This model isn't just a theoretical concept. It has tangible benefits in the realm of chemistry. By using the VSEPR model, chemists can predict the shapes of molecules that form during various chemical reactions. This knowledge is invaluable in understanding the properties and behaviors of these molecules. Imagine being able to anticipate how a molecule will behave based on its structure. This predictive power aids in fields like drug development, materials science, and more. So, as you can see, the VSEPR model isn't just about balloons and repulsion. It's a tool that empowers us to decode the intricate language of molecular architecture. Hello, dear students. Today, we're going to delve into the captivating world of electron domains and their arrangement. You see, electrons are like tiny particles that carry negative charges, and they play a crucial role in chemical bonding. When we have a certain number of these electron domains around an atom, we want to arrange them in a way that minimizes the repulsions between them. Why? Because like charges repel each other, and we want to find the most stable configuration possible. Imagine it like arranging seats in a theater to ensure everyone has enough space and doesn't bump into each other. This optimal arrangement has a significant impact on the overall structure of molecules. So, let's explore how we determine this arrangement and ensure that the repulsions among electron domains are minimized. Are you excited? Let's move on to our next topic. Welcome back, curious minds. Our journey continues with the introduction of a powerful concept called VSEPR theory, which stands for valence shell electron pair repulsion. Remember, the valence shell is the outermost energy level of an atom, and it's where the action happens when atoms come together to form molecules. The theory is simple but incredibly insightful. It tells us that electron pairs in the valence shell repel each other, and this repulsion influences the three-dimensional arrangement of atoms in a molecule. By predicting how these electron pairs will arrange themselves to minimize repulsions, we can actually predict the shape of molecules. It's like envisioning how a puzzle fits together based on the pieces' shapes and how they interact. This theory is a game-changer in understanding molecular geometry. Let's move forward and explore some real-world examples. Hello again, inquisitive minds. Now that we have a solid understanding of the VSEPR theory, let's put it into action. We'll explore real-world examples where we apply the theory to determine molecular geometry. Imagine you're planning a picnic, and you need to arrange the picnic baskets in a way that maximizes space and minimizes bumping into each other. Similarly, we'll apply the VSEPR theory to figure out how electron domains arrange themselves in various molecules. As a result, we can predict the shape of the molecules. From linear to trigonal pyramidal to tetrahedral. These molecular shapes give us insights into how atoms bond and interact. It's like solving a 3D puzzle with a set of rules. So, get ready to dive into some exciting examples as we journey further into the world of molecular geometry. Welcome, dear students. Today's lesson is going to be truly fascinating as we delve into the intriguing world of electron domains and their connection to something as familiar as balloons. Yes, you heard that right. Just like how balloons have preferred arrangements, electron domains exhibit similar patterns. When we have two electron domains, they arrange themselves linearly, much like balloons in Figure 9.5. Likewise, 3 electron domains adopt a trigonal planar orientation, and 4 electron domains take on a tetrahedral arrangement. Now, let's take a closer look at these arrangements as we move on. As we explore further, let's understand the specifics of electron domain geometries. 2 electron domains align themselves linearly, creating a simple yet elegant arrangement. When we have 3 electron domains, they prefer a trigonal planar orientation, and with 4 electron domains, the arrangement becomes tetrahedral. But what about cases with more than 4 electron domains? For those intricate arrangements, I encourage you to take a look at Table 9.1. It provides a comprehensive summary of these geometries, allowing you to grasp the complete picture. Now, let's put our observation skills to the test and compare the geometries we've been discussing. Take a look at the geometries listed in Table 9.1 and those presented in Figure 9.3. What do you notice? Yes, you're absolutely right, they are the same. The linear, trigonal planar, and tetrahedral arrangements we discussed earlier align perfectly with the ones shown in Figure 9.3. This consistency emphasizes the remarkable patterns that govern electron domain orientations. Let's keep this insightful comparison in mind as we proceed. As we dig deeper into the subject, let's unravel the intricacies of these geometric analogies. Why do electron domains and balloons share these similar arrangements? The key lies in the interaction between electrons. You see, electrons repel each other due to their negative charges. This repulsion plays a crucial role in determining how they position themselves. The balloon analogy helps us visualize this concept by drawing parallels between the way balloons repel each other when squeezed into confined spaces and how electrons repel each other within an atom. This visualization aids us in understanding the driving forces behind these geometric patterns. Let's take a moment to recap what we've learned today. We explored the remarkable similarities between electron domains and balloons, observing how their preferred geometries align. This connection is rooted in the repulsive nature of electrons within atoms. Our journey into this captivating realm is just beginning. In our next lessons, we'll dive even deeper into the intricacies of electron domains and their impact on molecular shapes. Remember, a solid grasp of these concepts is essential for a comprehensive understanding of chemistry. Keep your curiosity alive, and get ready to explore more in the lessons to come. Hello again, eager minds. Today, we're delving into the fascinating concepts of molecular and electron domain geometries. To put it simply, the way electron domains are arranged around the central atom of an ABN molecule or ion is what we call its electron domain geometry. It's like arranging the seating at a dinner table. It's all about finding the right spots for everyone. But wait, there's more. The molecular geometry steps in to give us the arrangement of only the atoms in a molecule or ion. Any non-bonding pairs of electrons in the molecule aren't part of this description. Imagine this as arranging the dishes on that same dinner table, without considering the empty chairs. These geometries play a crucial role in understanding the shapes of molecules and their properties. Let's move on to our next topic to uncover more about this intriguing topic. Hello, dear students. Today, we're going to embark on a fascinating journey into the world of predicting the shapes of molecules and ions using a powerful model called VSEPR. So, what's VSEPR, you ask? Well, it stands for valence shell electron pair repulsion, and it's like a secret code that helps us decipher how atoms arrange themselves in a molecule. Now, let's uncover the steps to predict these shapes and bring clarity to this concept. Welcome, students. Today, we're diving into the fascinating world of chemistry. Pay close attention as we take our first step in this enlightening journey. Alright, my bright minds. The first step in our journey is drawing the Lewis structure. This structure helps us visualize the arrangement of atoms and their valence electrons. Remember, each non-bonding electron pair, single bond, double bond, and even a triple bond counts as one electron domain. Got that? Let's move on. Step 2. Everyone. Once we've counted those electron domains, we need to arrange them around the central atom. The key here is to minimize repulsions between these electron domains. Think of it like friends finding the best arrangement to sit around a table. You can consult Table 9.1 for common arrangements that make this easier. Remember, we're like molecular architects here. Alright, time for the third step, my inquisitive learners. We're diving into molecular geometry now. This is where we look at the arrangement of atoms, both bonded and lone pairs. What's crucial here is to recognize the shape using common names like tetrahedral or trigonal planar. So, just like sculptors, we're carving out the actual shape of the molecule. And there you have it. Curious minds. We've taken a deep dive into the VSEPR model, a tool that lets us decipher the intricate shapes of molecules and ions. Remember, it's all about predicting shapes based on electron repulsions. Lewis structures, electron domain geometry, and molecular geometry are our trusty guides. Don't forget the impact of lone pairs, they play a significant role in shaping molecules. Keep exploring the world of chemistry, and remember that every shape tells a unique story. Welcome back, students. Today, we're delving into the world of molecular geometries and the intriguing concept of the octet rule. Our journey begins with Table 9.2, which provides a comprehensive summary of possible molecular geometries when an ABN molecule has 4 or fewer electron domains around atom A. These geometries play a crucial role in understanding the shapes commonly observed in molecules and ions that adhere to the octet rule. This rule guides us in predicting the arrangement of atoms in a molecule and their bonding patterns. Keep in mind that these molecular geometries are essential building blocks for comprehending the intricate world of chemical structures. Now, let's move on to our next exciting topic. Good day, students. In today's lesson, we're delving into the world of molecular geometry, using a powerful concept called the VSEPR model. VSEPR stands for valence shell electron pair repulsion, and it helps us predict the three-dimensional arrangement of atoms in a molecule. Our focus will be on understanding how this model applies to the NH3 molecule. So, let's get started by breaking down the steps outlined in Figure 9.6. Alright, students, let's roll up our sleeves and dive into the first step of the VSEPR model applied to NH3. As we can see in the Lewis structure of NH3, there are 3 bonds and 1 non-bonding pair. This gives us a total of 4 electron domains. Now, if we consult Table 9.1, we learn that NH3M's electron domain geometry is tetrahedral. Keep in mind that this electron domain geometry considers all electron domains, including both bonds and non-bonding pairs. Moving right along, let's transition from electron domain geometry to molecular geometry. We're interested in the arrangement of atoms within the molecule itself. To do this, we focus only on the three NH bond domains, disregarding the non-bonding pair for now. This shift in perspective takes us from tetrahedral to trigonal pyramidal geometry. The non-bonding pair's presence causes this alteration, leading to the distinctive shape we observe in molecules like NH. Let's take a moment to grasp the fascinating connection between electron domain and molecular geometry. Imagine a tetrahedral arrangement of electron domains. Now, if we remove one atom from this tetrahedral structure, what do we get? Yes, a trigonal pyramidal arrangement emerges. This is beautifully demonstrated in the middle drawing of figure 9.4. So, when we predict a trigonal pyramidal molecular geometry for NH3, it's rooted in the tetrahedral arrangement of its four electron domains. As we conclude today's lesson, let's recap the core concepts we've explored. The VSEPR model serves as a powerful tool to foresee the three-dimensional shape of molecules by considering electron domains. Non-bonding pairs play a significant role in determining molecular geometry, as we've seen with NH3's trigonal pyramidal shape. Remember, the interplay between electron domain geometry and molecular geometry offers us intriguing insights into the world of molecules. Keep up the curiosity, and we'll continue our journey into the mysteries of chemistry. Hello, dear students. Today, we're delving into the captivating realm of molecular geometry and bond angles. Our second topic introduces us to the intriguing trigonal pyramidal molecular geometry. This geometry is actually built upon the foundation of a tetrahedral electron domain geometry. Now, what's fascinating is that the ideal bond angle within this geometry is 109.5 degrees. But here's where it gets even more intriguing: when the surrounding atoms and electron domains aren't identical, these bond angles can deviate from their ideal values. So, remember, the symmetrical arrangement of atoms greatly influences the angles formed between the bonds. As we journey further, you'll discover how these subtle variations play a significant role in the overall structure and behavior of molecules. Hello again, students. Now, let's venture into the world of molecular structure and take a closer look at the CO molecule. In the Lewis structure of CO, we can observe two electron domains surrounding the central carbon atom. These domains are each represented by a double bond. Imagine these bonds as pathways for electrons, forming a unique arrangement that shapes the molecule. This structure has fascinating implications for the properties and behavior of CO. Let's continue delving into the captivating realm of chemical structures and their significance. Hello, dear students. Today, we're delving into the fascinating realm of electron domain and molecular geometry. Let's start by focusing on a scenario where two electron domains are present around a central atom. As per the information in Table 9.1, when we have two electron domains, they arrange themselves in a linear electron domain geometry. But how does this arrangement influence the molecular geometry? Well, since there are no non-bonding pairs of electrons, the resulting molecular geometry remains linear as well. Imagine this as a kind of molecular puzzle, where the pieces just align in a straight line. Consequently, the bond angle between the atoms, such as in the case of the O-CO bond, is a perfectly straight 180 degrees. Isn't it intriguing how the arrangement of electron domains influences the overall structure of molecules? Let's move on to our next topic and continue our exploration of the captivating world of chemistry. Welcome back, students. In our quest to understand chemical bonding and molecular shapes, We're going to explore a refinement to the VSEPR model that explains deviations from ideal geometries. As you recall, the VSEPR model helps us predict molecular shapes based on the number of electron domains around a central atom. Let's delve into some interesting examples: methane, ammonia, and water. Although all three molecules have a tetrahedral electron domain geometry, their actual bond angles differ slightly. In methane, Kethane, the bond angles are about 109.58 degrees. For ammonia, they are around 107.8 degrees. And in water, the bond angles measure about 104.58 degrees. These deviations arise due to the effects of non-bonding electrons and multiple bonds. Now, let's move on to the specifics of these molecules and the factors influencing their bond angles. Alright, dear students, let's start by examining methane closely. This molecule consists of a central carbon atom surrounded by 4 hydrogen atoms. The VSEPR model predicts a perfect tetrahedral arrangement due to the 4 bonding pairs. However, in reality, the bond angles deviate slightly from the ideal 109.5 degrees. This happens because the electron pairs repel each other, creating a subtle distortion in the angles. So, in methane, the actual bond angle measures approximately 109.58 degrees. Remember, it's the interactions between the electrons that lead to these deviations. Moving on to ammonia, NH3, students. Here, we have a nitrogen atom at the center, with 3 hydrogen atoms bonded to it. The VSEPR model, again, predicts a tetrahedral arrangement due to the 3 bonding pairs. However, there's an interesting twist: there's also a non-bonding pair of electrons. This non-bonding pair exerts its influence and creates a repulsion effect on the bonding pairs. As a result, the bond angles in ammonia deviate from the ideal tetrahedral angle. The actual bond angle for ammonia is approximately 107.8 degrees. The non-bonding pair's presence significantly affects the overall geometry. Let's now explore water. HO, students. This molecule showcases a central oxygen atom and 2 hydrogen atoms bonded to it. As per the VSEPR model, the arrangement should be tetrahedral due to the 2 bonding pairs. However, here's the catch: there are not 1, but 2 non-bonding pairs of electrons around oxygen. These non-bonding pairs exert a significant repulsion on the bonding pairs, causing the bond angles to deviate even further from the ideal angle. In water, the actual bond angle measures about 104.58 degrees. This case demonstrates how non-bonding electrons can play a crucial role in shaping molecular geometry. Let's wrap up our discussion, students. Today, we've journeyed through the effects of non-bonding electrons and multiple bonds on bond angles in molecular geometry. Remember, while the VSEPR model provides us with ideal geometries, real molecules often deviate slightly due to the presence of non-bonding pairs and the effects of electron repulsions. We explored this phenomenon through examples of methane, ammonia, and water. It's crucial to understand these deviations as they offer us insights into the intricate world of chemical bonding and molecular shapes. Keep these concepts in mind as we continue our exploration of the fascinating realm of chemistry. Hello again, students. Let's delve deeper into the world of chemical bonding and electron density. As we've learned, multiple bonds, such as double and triple bonds, contain a higher electronic charge density compared to single bonds. This higher density results in what we call enlarged electron domains. To help visualize this concept, consider the Lewis structure of a molecule like phosgene, which has the formula Cl2CO. In this molecule, you can see multiple bonds between carbon and oxygen, as well as between carbon and chlorine atoms. These multiple bonds indicate the presence of larger electron clouds around the atoms involved. Now, let's move forward and explore more intriguing aspects of chemical structures. Welcome back, everyone. Today, we're going to take a closer look at the Lewis structure of a specific molecule, phosgene, with the chemical formula ClCO. In this compound, you can see the arrangement of atoms. 2 chlorine atoms, chlorine, 1 carbon atom, carbon, and 1 oxygen atom, oxygen. What's intriguing about this structure are the multiple bonds present. There's a double bond, C=O, between carbon and oxygen, as well as a single bond, CCl, between carbon and chlorine. These multiple bonds are the key to understanding the concept of enlarged electron domains. As we examine the Lewis structure diagram, observe how the electron clouds around the carbon and oxygen atoms are more extensive due to the multiple bonds. This increased electron density plays a crucial role in various chemical interactions and reactions. Now, let's continue our journey into the world of chemical structures and their fascinating properties. Great to see you all engaged. Today, we're uncovering the significance of electron density in chemical interactions. As we've established, multiple bonds lead to enlarged electron clouds around atoms. This electron density directly impacts the strength of chemical bonds and the behavior of molecules. With larger electron clouds, atoms can develop partial charges, affecting their reactivity. Take a moment to consider molecules with single and multiple bonds. The distribution of electron clouds greatly influences their behavior. For instance, molecules with multiple bonds are often more reactive due to the higher electron density around the atoms involved. This reactivity plays a vital role in various chemical reactions, allowing for the creation of new substances. Let's now proceed to explore more captivating aspects of chemical bonding and its implications. Hello, inquisitive minds. We're about to uncover the real-world applications of the concepts we've been discussing. Electron density, especially in the context of multiple bonds, plays a pivotal role in numerous industries. Consider the field of pharmaceuticals. The understanding of electron density guides chemists in designing molecules with desired properties. Similarly, the realm of materials science benefits from the reactivity enhanced by multiple bonds, allowing for the creation of innovative materials. And let's not forget the impact on nanotechnology and electronics, where precise control over electron density leads to groundbreaking advancements. As we move forward, keep in mind that the world of chemistry is intricately connected to the technological progress we experience every day. Stay curious, and let's continue our exploration. Hello again, students. Let's now delve into the intriguing world of electron domains and the forces that arise within different types of bonds. Specifically, we'll explore the differences between electron domains in multiple bonds and those in single bonds. Imagine electron domains as regions of electron density around atoms that participate in bonding. When we consider multiple bonds, such as double or triple bonds, the electron domains within them exert a much stronger repulsive force on the adjacent electron domains. This force is more pronounced than what we observe in the case of electron domains within single bonds. This phenomenon has a profound impact on the shape and structure of molecules. To gain a better understanding, let's visualize this concept in the accompanying image. Now, let's proceed to our next exciting topic. Hello, dear students. Today, we're delving into the intriguing world of molecular geometries, particularly those involving atoms with expanded valence shells. As we venture further down the periodic table, we encounter atoms from period 3 and beyond that possess more than 4 electron pairs in their valence shells. This phenomenon leads to the formation of molecules with unique structures. When a central atom is surrounded by 5 electron domains, it adopts a trigonal bipyramidal geometry. Imagine this geometry as a central atom with 3 atoms arranged in a flat triangle and 2 atoms at the top and bottom, like a bipyramid. Now, for the more complex cases, when a central atom is encircled by 6 electron domains, it adopts an octahedral geometry. Picture this geometry as a central atom with 6 surrounding atoms at the corners of an octahedron, a shape resembling 2 pyramids stuck together at their bases. Isn't chemistry fascinating? Let's move on to our next captivating topic. Welcome, students. Today, we're delving into the intriguing world of electron domain geometry. Our focus is on a specific arrangement known as the trigonal bipyramid. This geometry involves 5 electron domains, and it's a structure that provides remarkable stability. Imagine it as 2 trigonal pyramids sharing a common base. Now, what's fascinating about the trigonal bipyramid is that it offers 2 distinct types of positions, axial and equatorial. In this arrangement, we have 2 electron domains pointing toward axial positions and 3 electron domains pointing toward equatorial positions. Visualize this geometry in your mind as we move on to understand the angles and interactions within this arrangement. Alright, students, let's dive deeper into the angles within the trigonal bipyramid arrangement. Remember, we have 2 types of positions, axial and equatorial. Each axial domain forms a 90-degree angle with any equatorial domain. This means that the electron domains pointing toward axial positions are separated by 90 degrees. On the other hand, when it comes to equatorial domains, they form a 120-degree angle with each other. Additionally, each equatorial domain forms a 90-degree angle with the axial domains. These angles play a crucial role in determining the overall shape and stability of the trigonal bipyramid. Now, let's explore more aspects of electron domain geometry. Great job, students! As we unravel the mysteries of electron domain geometry, it's important to understand how electron domains interact and contribute to the stability of molecules. In the trigonal bipyramid, these interactions play a significant role. One key observation is that electron domains in equatorial positions experience less repulsion compared to those in axial positions. The reason behind this lies in the angles we discussed earlier. The greater separation between equatorial domains, at 120 degrees, leads to reduced repulsion. This balanced distribution of repulsive forces contributes to the overall stability of the trigonal bipyramid arrangement. Isn't it fascinating how even at the microscopic level, these interactions have a profound impact on molecular structures? Let's continue our journey of discovery. Welcome back, eager learners. Now that we've grasped the concept of trigonal bipyramid geometry, let's see how it applies to real molecules. One such example is phosphorus pentafluoride, often denoted as PF5. In this molecule, a central phosphorus atom is surrounded by 5 fluorine atoms. If we examine the arrangement of these atoms, we find that it perfectly matches the trigonal bipyramid geometry we've been exploring. This molecule serves as a tangible example of how the principles we've discussed today manifest in the real world. Remember, understanding these molecular geometries helps chemists predict how molecules will interact and behave in various chemical reactions. Keep up the enthusiasm as we delve further into the world of chemistry. Hello, students. Today, we're delving into the realm of molecular orbital theory and exploring the intriguing interactions between atomic orbitals. So, let's dive right in. Molecular orbital theory is a captivating concept that helps us understand how atoms come together to form molecules and how their electron orbitals merge to create molecular orbitals. In the context of this theory, let's consider the interactions between O and N atomic orbitals in a molecular environment. Now, when O and N atomic orbitals combine to form molecular orbitals, interesting things happen. Specifically, let's talk about the S2s MO, where the atomic orbitals of O and N come into play. Due to the energy levels of these atomic orbitals, the resulting S2s MO isn't an equal mixture of the two atoms, as we observed in homonuclear diatomic molecules. Instead, the contribution from O is slightly greater than from N. This disparity occurs because the O2's atomic orbital is energetically closer to the S2s MO compared to the N2's atomic orbital. Similarly, let's explore the S2's anti-bonding MO, where we see a different pattern. This anti-bonding MO is more heavily weighted toward the N atom. Why? Well, it turns out that this particular anti-bonding MO closely matches the energy level of the N2's atomic orbital. In summary, the energy levels of atomic orbitals play a crucial role in determining the contributions and interactions between different atoms in molecular orbitals. This intricacy leads to fascinating variations in molecular properties. As we journey deeper into this topic, Remember that molecular orbital theory is an essential tool for understanding the complex world of chemical bonding and molecular structure. Get ready to explore more in the coming topics. Good day, students. Today, we're delving into the intriguing world of electron domain geometry and molecular shapes. Let's begin by understanding the concept of electron domain geometry. When an atom is surrounded by electron domains, it adopts a specific arrangement that affects its molecular shape. In the case of 6 electron domains, the most stable geometry is the octahedron. Picture an octahedron as a polyhedron with 6 vertices and 8 equilateral triangle faces. Now, imagine our atom positioned at the center of this octahedron, with its electron domains extending towards the 6 vertices. This arrangement leads to bond angles of 90 degrees, and importantly, all 6 vertices are equivalent in an octahedral geometry. This arrangement of electron domains has profound implications for the resulting molecular shape. Let's move on to the next topic to explore this further. Welcome back, students. In our last topic, we discussed the octahedral electron domain geometry. Now, let's focus on a specific scenario involving atoms with 5 bonding electron domains and 1 non-bonding domain. In this case, the non-bonding domain can be positioned at any of the 6 vertices of the octahedron. No matter where it's placed, the resulting molecular shape is always a square pyramidal geometry. Picture a pyramid with a square base, and you'll get a sense of how the atoms arrange themselves in this configuration. The bond angles remain at 90 degrees, and the symmetry of the arrangement leads to this distinctive shape. But what happens when we introduce more non-bonding domains? Let's explore that in the next topic. Great job, students! In our previous topic, we explored the square pyramidal molecular geometry. Now, let's shift our focus to another intriguing arrangement, the square planar molecular geometry. This geometry arises when an atom has not 1, but 2 non-bonding electron domains. To minimize repulsions between these domains, they are strategically placed on opposite sides of the octahedron. This arrangement leads to the distinctive square planar molecular geometry. Imagine a flat square with atoms positioned at its corners and you'll have a good visual representation. This geometry showcases the intricate balance between electron repulsions and the resulting molecular shape. As we continue our journey, keep in mind that the arrangement of electron domains has a direct impact on molecular properties. Hello, dear students. Today, we're delving into an intriguing topic that expands upon our understanding of molecular shapes. Up until now, we've explored molecules with single central atoms, examining their geometries using the VSEPR model. But what happens when molecules become more complex? Can we still use the same model? The answer is a resounding yes. The VSEPR model remains a powerful tool for predicting the shapes of even larger molecules. To illustrate this, let's consider the acetic acid molecule, which has the formula C8. This molecule consists of multiple atoms, including carbon, hydrogen, and oxygen, arranged in a specific configuration. By applying the principles of the VSEPR model, we can decipher its shape and gain valuable insights into its geometry. So, buckle up as we journey into the world of intricate molecular structures. Greetings, eager learners. Let's dive deeper into the acetic acid molecule, also known by its chemical formula CHCOOH. This compound showcases how the VSEPR model can be applied to more intricate structures. At its core, the acetic acid molecule contains a central carbon atom, surrounded by hydrogen and oxygen atoms. The arrangement of these atoms, as well as any lone pairs of electrons, plays a pivotal role in determining the molecule's overall shape. By employing the VSEPR model, we can make insightful predictions about the molecular geometry of acetic acid. The model guides us in understanding how electron pairs arrange themselves around the central atom to minimize repulsion. As we navigate through this example, remember that the VSEPR model remains an indispensable tool for uncovering the mysteries of molecular shapes. Welcome back, inquisitive minds. Let's unveil the captivating geometry of the acetic acid molecule, as foretold by the VSEPR model. Remember, the VSEPR model helps us predict molecular shapes by considering the arrangement of both bonding and non-bonding electron pairs around the central atom. In the case of acetic acid, the central carbon atom is the focal point. Due to the arrangement of its surrounding atoms and lone pairs, the carbon atom exhibits a tetrahedral geometry. This means that the molecular structure around carbon resembles a pyramid with 3 hydrogen atoms and 1 oxygen atom forming the base. However, the oxygen atoms each have a bent geometry due to the presence of lone pairs. It's the delicate dance of electron pair repulsion that guides these shapes, ensuring stability within the molecule. Marvel at how these principles extend to even complex molecular structures. Hello, dear students. Today, we're delving into the realm of molecular geometry, using a tool known as the VSEPR model. VSEPR, which stands for valence shell electron pair repulsion, is a fascinating concept that helps us predict the shapes of molecules. Imagine electron pairs as tiny magnets that either attract or repel each other. This interaction determines the overall geometry of a molecule. Now, let's apply this idea to our given arrangement of atoms, carbon and oxygen. We'll analyze how the VSEPR model helps us anticipate the geometry around each carbon and oxygen atom. Get ready to unlock the secrets of molecular structures. Welcome back, enthusiastic learners. Today, we're focusing on geometry prediction, and we're starting with our trusty carbon atom in the arrangement. Surrounding the carbon atom are 4 hydrogen atoms. Now, when we apply the VSEPR model, it tells us that the geometry around the carbon atom is tetrahedral. Picture a pyramid with the carbon atom at the center and the hydrogen atoms at the corners. Why does this happen? Electron pairs, like students in a crowded room, want to maximize their distance to minimize repulsion. This creates the tetrahedral shape. So, remember, geometry is all about finding that balance between attraction and repulsion. Greetings, knowledge seekers. Let's shift our attention to the oxygen atom in our arrangement. This atom is flanked by 2 carbon atoms. Applying the VSEPR model here reveals a linear geometry. Imagine the oxygen atom at the center and the carbon atoms on either side, like a straight line. The reason for this linear shape lies in electron pair repulsion. The electron pairs want to be as far apart as possible, which in this case, means pushing to opposite sides. As you can see, geometry isn't just a shape. It's a result of the intricate dance of electrons. Let's keep exploring. Hello again, curious minds. Let's take a moment to appreciate the power of the VSEPR model in unraveling molecular mysteries. By examining our arrangement of carbon, oxygen, and hydrogen, we've uncovered the tetrahedral geometry around carbon and the linear geometry around oxygen. These shapes aren't just random. They arise from the fundamental principles of electron pair repulsion. Just like people trying to find their space in a crowded room, electrons arrange themselves to minimize repulsion and find stability. So, next time you encounter a molecule, remember that its shape holds a story of these electron interactions. Keep up the great work, and let's continue our exploration of the captivating world of chemistry. Welcome back, students. Today, we're delving into the captivating realm of molecular architecture and its profound impact on substances and reactions. Imagine molecules as intricate puzzles. Their shape, size, and the strength of bonds they form dictate the unique properties of each substance. This phenomenon is beautifully exemplified in the world of biochemical reactions. Let's take a closer look at something truly remarkable. Consider drugs. They are composed of molecules, and even the slightest shifts in the 3-dimensional arrangement of atoms can yield massive consequences. Our visual aid showcases 2 molecules, namely, S-naproxen and R-naproxen, each with the same chemical formula and identical bonds. However, upon closer examination, you'll notice a crucial difference. The positioning of an H and a CH3 group is reversed in one of them. Astonishingly, the compound with this slight modification, labeled as S-naproxen, is prescribed to alleviate arthritis pain. On the other hand, its counterpart, R-naproxen, is not only ineffective but harmful, causing liver poisoning. These molecules belong to a fascinating group known as enantiomers, a subset of structural isomers. Enantiomers possess distinct arrangements, and we'll explore more about them in the upcoming chapters. It's worth noting that the pharmaceutical industry invests significant effort into crafting, isolating, and purifying specific isomers of compounds due to their diverse effects. Now, let's continue our journey by unraveling more about the intricate world of molecular structures and their impacts on the chemistry of life. Hello again, students. I hope you're all excited to embark on this journey of understanding molecular polarity. By the time we reach the end of this section, you'll have a solid grasp of how to determine whether a molecule is polar or nonpolar. Now, let's jump in. Molecular polarity is a crucial concept in chemistry. It's all about understanding how the arrangement of atoms and bonds within a molecule can result in either a polar or nonpolar nature. There are a few key factors that influence whether a molecule is polar or nonpolar, and one of them is its geometry. The shape of a molecule plays a significant role in determining its overall polarity. Additionally, individual bond-dipole moments, which result from differences in electronegativity between bonded atoms, contribute to the overall polarity of a molecule. Keep in mind that a molecule's polarity affects various properties, including its interactions with other molecules. Now, let's delve deeper into the relationship between geometry, bond-dipole moments, and molecular polarity. Alright, my curious students, let's focus on the impact of molecular geometry on polarity. The arrangement of atoms in a molecule's structure has a significant say in whether it's polar or nonpolar. Imagine a molecule as a puzzle, where each atom has its designated spot. Now, if a molecule has a symmetrical geometry, meaning the atoms are distributed evenly around a central atom, it's likely to be nonpolar. On the other hand, if the geometry is asymmetrical, with atoms clustering around the central atom in an uneven manner, the molecule tends to be polar. Remember, lone pairs of electrons can also influence a molecule's shape, making it deviate from the expected geometry. So, whether a molecule has lone pairs or not, and how they're positioned, can greatly impact its polarity. Let's move forward and explore the practical application of these concepts. Great job, students! Now, let's uncover the fascinating world of bond-dipole moments. These moments arise from differences in electronegativity between atoms in a bond. Electronegativity is like a tug-of-war between atoms for shared electrons. When one atom has a stronger pull, it creates an uneven distribution of electron density. This results in a partial positive charge on one end of the bond and a partial negative charge on the other end. These charges don't cancel each other out due to the vector nature of these moments. So, when we add up all the bond-dipole moments within a molecule, we get a net molecular dipole moment. This net dipole moment indicates whether the molecule as a whole is polar or nonpolar. Stay with me, students, as we're about to tie these concepts together. You're doing fantastic, my attentive learners. Now, let's walk through the steps to determine whether a molecule is polar or nonpolar. First, examine the molecule's geometry. If it's symmetrical, there's a good chance it's nonpolar. If it's asymmetrical, polarity is more likely. Next, assess the individual bond polarities. If the atoms within a bond have a significant difference in electronegativity, that bond is likely polar. Finally, consider the molecular dipole moment. If the bond-dipole moments within the molecule don't cancel each other out due to asymmetry, you'll end up with a net dipole moment and, therefore, a polar molecule. It's like figuring out the puzzle of polarity. As we wrap up, remember that this understanding is crucial for predicting how molecules interact and behave in various situations. You're well on your way to becoming experts in molecular polarity. Hello again, dear students. Let's continue our exploration of molecular structures and delve into the intriguing world of bond polarity and dipole moments. These topics might sound a bit complex, but fear not, as we'll break them down step by step. Remember our discussions in section 8.4? Well, it's time to revisit them. Bond polarity, as you might recall, gauges how evenly electrons are shared between two atoms in a bond. Now, here's an important tidbit. As the electronegativity difference between these atoms increases, the bond polarity also increases. Electronegativity plays a crucial role in determining how the electrons are attracted to the atoms involved. But what about dipole moments? Think of them as a measure of charge separation within a diatomic molecule. The greater the charge separation, the higher the dipole moment. This concept gives us insights into the molecular behavior. Let's proceed and uncover more about these intriguing molecular attributes. Greetings, inquisitive minds. Today, we're immersing ourselves further into the world of chemical bonding. One key player in this realm is electronegativity. Electronegativity measures an atom's tendency to attract electrons in a chemical bond. Different atoms exhibit varying levels of electronegativity. When two atoms with differing electronegativities come together to form a bond, the more electronegative atom tends to pull the electrons closer, resulting in an uneven sharing of the electron cloud. This gives rise to bond polarity. Depending on the electronegativity difference, bonds can be classified as polar covalent or even ionic. This polarity influences the behavior of molecules, impacting properties like solubility and reactivity. So, you see, electronegativity isn't just a number, it's a force that shapes molecular interactions. Let's move forward to our next intriguing stop. Welcome back, curious learners. Our journey brings us to the captivating concept of dipole moments and how they relate to charge separation within molecules. Imagine you have a molecule. Dipole moment is the measure of how much positive and negative charge are separated across the molecule. This charge separation occurs due to the electronegativity difference we discussed earlier. The greater the charge separation, the larger the dipole moment. It's like a tiny electric arrow pointing from the positive to the negative end of the molecule. Now, here's an interesting twist. Molecules with multiple bonds can have varying dipole moments for each bond, and these can even cancel each other out. This leads to nonpolar molecules, despite having polar bonds. Additionally, the molecular shape plays a role in determining the overall dipole moment. So, remember, even in the world of molecules, opposites attract. Ready to uncover more? Let's press on. Hello there, young minds. Today, we're delving into an exciting realm where molecules show us their hidden directional forces. Bond dipoles and dipole moments, as you'll soon learn, are more than just fancy terms. Imagine them as arrows with both size and direction. These vector quantities come into play when we explore the electrifying world of molecular polarity. When we examine a polyatomic molecule, its dipole moment is like the sum of its bond dipoles. But, remember, we can't ignore the size and direction of these individual dipoles when we're adding them up. It's just like adding numbers, where both their values and signs matter. Let's take an intriguing example: CO2. While the bond dipoles in CO2 are of equal magnitude, they point in opposite directions. Visualize this as adding 100 and then subtracting 100. What happens? They cancel out. The same concept applies to the bond dipoles, effectively making the dipole moment of CO2 zero. And here's the mind-boggling twist. Even though each bond is polar, the molecule as a whole is nonpolar due to its geometry. So, let's journey further into this captivating world of molecular dipoles and moments. Welcome back, dear students. Today, we're delving into the intriguing realm of molecular polarity, and our focus is on the remarkable molecule He2. As we venture into this topic, remember that molecular polarity plays a crucial role in various chemical interactions. Now, let's talk about He2's molecular structure. It's bent, like a little V-shaped molecule. This bent structure leads to something fascinating: two polar bonds. These bonds are identical and possess bond dipoles of equal magnitude. However, here's the twist. Since He2 is bent, the bond dipoles don't directly cancel each other out. This unique arrangement results in He2 having an overall non-zero dipole moment, which is measured as 185. This dipole moment makes He2 a polar molecule, and this is significant. When we look at He2, the oxygen atom carries a partial negative charge, while each of the hydrogen atoms carries a partial positive charge. This distribution of charges gives rise to the distinctive properties and behaviors of water. Let's move forward to explore more captivating concepts. Hello, dear students. In today's lesson, we're delving into the intriguing world of polar and nonpolar molecules. Get ready to explore some fundamental concepts that will deepen your understanding of molecular behavior. Let's begin by discussing the key differences between polar and nonpolar molecules, especially in relation to their bonds. Now, let's talk about an interesting phenomenon. Take a look at molecules like BF3 and CCl4. In these cases, the central atom is symmetrically surrounded by identical atoms. Surprisingly, even though these molecules contain polar bonds, they are classified as nonpolar molecules. This symmetry plays a crucial role in determining the overall polarity of the molecule. Now, let's explore a bit further. We have a group of molecules known as ABN molecules, where A represents the central atom and B represents surrounding atoms. These molecules can take on various shapes, such as linear, trigonal planar, tetrahedral, square planar, trigonal bipyramidal, and octahedral. Interestingly, certain symmetrical shapes within this group lead to nonpolar molecules, even when individual bonds might be polar. So, why is this understanding of symmetry and polarity important? It helps us comprehend the notion of nonpolar molecules better. Molecular symmetry has a significant impact on a molecule's overall polarity. Even though individual bonds within these molecules might possess polarity, the arrangement and symmetry of the surrounding atoms play a pivotal role in determining whether the molecule as a whole is polar or nonpolar. Alright, my bright students, let's sum up what we've learned today. We've explored the fascinating world of molecular polarity, where even molecules with polar bonds can be nonpolar due to their symmetrical arrangement. Remember, the symmetry of the surrounding atoms is a crucial factor in determining the overall polarity of a molecule. This lesson underscores the importance of considering both individual bond polarity and molecular symmetry when analyzing molecular behavior. Fantastic job grasping these concepts. Keep up the great work on your journey of scientific exploration. Hello, dear students. Today, we're delving into the intriguing realm of covalent bonding and the fascinating concept of orbital overlap. Imagine electron orbitals as pieces of a puzzle that fit together to create a chemical bond, much like the two sides of a zipper that merge to form a secure fastening. Just as a zipper requires compatible size and shape of its components, so does the formation of a chemical bond. This compatibility ensures the stability of the bond. As we progress through this section, you'll gain a comprehensive understanding of how electron orbitals overlap and contribute to the formation of molecules. Let's continue our journey of discovery. Welcome back, enthusiastic learners. Today, we're focusing on covalent bonds and the remarkable sharing of electrons between atoms. This sharing isn't just a random act, it's driven by a desire for stability. As atoms share electrons, they achieve more balanced and stable electron configurations, akin to reaching a state of contentment. Through covalent bonding, atoms come together to form marvelous molecular compounds, each with its own unique properties and functions. As we proceed, you'll discover the intricacies of how atoms cooperate to create these bonds. Greetings, inquisitive minds. Today, we're taking a deeper look at the relationship between orbital overlap and the strength of covalent bonds. The extent of orbital overlap directly influences how strong the resulting bond will be. There are two primary types of orbital overlap, sigma and pi bonds. Sigma bonds emerge when two orbitals directly align, head-on. On the other hand, pi bonds form through the sideways overlap of p orbitals. These distinctions in overlap contribute to the unique properties of various molecules. So, as we progress, remember that the way electrons share space impacts the robustness of the bonds formed. Hello again, eager learners. Our journey through covalent bonding takes us to the captivating realm of molecular shapes and orbital hybridization. Imagine atoms as artists, skillfully mixing their atomic orbitals to create new hybrid orbitals. These hybrid orbitals aren't just random combinations. They adapt in shape to minimize repulsion between electrons and maximize the stability of the molecule. This artistic process results in various molecular shapes, each with its own unique attributes. Today, we'll explore examples of hybridization, such as sp, sp2, and sp3 hybrid orbitals, and discover how they influence the structures of molecules. So, let's dive in and uncover the mysteries of molecular geometry. Greetings, bright minds! Today, let's tie together everything we've learned about covalent bonding and molecular structure by drawing a captivating analogy. Think of covalent bonds as the zippers of the molecular world. Just as a zipper's components need to be compatible and properly connected to create a secure closure, atoms must find the right fit for their electron orbitals to form stable bonds. Just as a zipper holds things together, these bonds stabilize molecules. Relating complex concepts to everyday experiences helps us better understand and appreciate the world of chemistry. So, keep these analogies in mind as you continue your exploration of the wonders of chemical bonding. Well done, enthusiastic learners! As we conclude our exploration of covalent bonding and orbital overlap, I hope you're feeling confident in your understanding of these fundamental concepts. We've journeyed through the intricate world of electron sharing, orbital alignment, and molecular geometry. Remember, just as electrons come together to form stable bonds, we've come together to form a deeper connection with chemistry. Whether it's the analogy to zippers or the intricacies of orbital hybridization, your grasp of these concepts will be an invaluable foundation for your further studies. So keep that curiosity burning, and let's continue unraveling the mysteries of science together. Welcome back, dear students. Today, we're embarking on a fascinating journey into the realm of chemical bonding. Specifically, we're delving into the intriguing concept of covalent bonding, which plays a crucial role in shaping the molecular world around us. In Lewis theory, covalent bonding occurs when atoms generously share electrons. This sharing, in turn, results in the concentration of electron density right between the participating nuclei. Visualizing this process becomes even more captivating when we turn to valence bond theory. Imagine the interaction as a dance between atoms, where their valence atomic orbitals overlap, or share space. This delightful overlap allows electrons, each with an opposite spin, to find a cozy home between the nuclei, effectively forming what we call a covalent bond. So, remember, it's the dance of shared electrons that holds molecules together, and this dance is guided by the interplay of valence atomic orbitals. Now, let's dive deeper into the intricacies of covalent bonding and explore its impact on the world of chemistry. Greetings, inquisitive minds! Today's lesson has us focusing our attention on valence bond theory and the incredible dance of electrons that leads to covalent bond formation. Imagine this theory as our tool for peeking into the world of atoms forging connections. When atoms come together, their valence atomic orbitals come into play. These orbitals are like special arenas where electrons hang out. Picture two atoms edging closer, allowing their valence orbitals to overlap, much like an elegant ballet. This overlap is the critical juncture where the magic of covalent bonding unfolds. Electrons from each atom find themselves sharing this common space, spinning in opposite directions. The result? A strong covalent bond that holds the atoms together in a molecule. So, my brilliant students, remember that covalent bonds are all about sharing and overlapping, a dance of electrons that makes the world of chemistry a marvel to explore. As we move forward, we'll delve deeper into this dance and explore its implications. Null. Welcome back, knowledge seekers. Let's take a moment to recap our exhilarating journey into the world of covalent bonding. We've explored the core principles of Lewis theory, where electron sharing leads to the concentration of electron density between nuclei. Our visualization tool, valence bond theory, lets us witness the graceful overlap of valence atomic orbitals, paving the way for electron pairs to emerge and covalent bonds to be born. These bonds bring about a sense of stability and energy harmony within molecules, much like a well-choreographed dance. The concentration of the electron cloud in the shared space directly influences the strength of the bond itself. As we conclude this segment, keep in mind that the intricate dance of electrons is at the heart of the chemical world's beautiful symphony. Our journey continues, so stay curious and let's dive further into the captivating realm of chemistry. Welcome back, dear students. Today, we're delving into the intriguing realm of molecular formation using the valence bond theory. This theory provides us with a deeper understanding of how atoms come together to create molecules. Imagine atoms as puzzle pieces, and molecules as the completed puzzles. Our journey starts with an example of the formation of a hydrogen molecule, H2. In this scenario, each hydrogen atom possesses a single electron housed in a 1s orbital. Now, as these orbitals overlap, something magical happens. The electron density gets concentrated between the nuclei, creating a zone of electron sharing. And guess what? Because these electrons are attracted to both nuclei, they play a crucial role in holding the atoms together. This attraction results in the formation of a covalent bond. Let's take a visual journey through this process in our next topic. Great job keeping up, students! In the previous topic, we introduced the concept of electron density concentration. Now, let's delve deeper into this fascinating phenomenon. Imagine the region between the nuclei of two interacting atoms. This region becomes a hotbed of electron activity, with electron density accumulating there. What's even more astonishing is that these electrons are drawn towards both nuclei simultaneously. This dual attraction plays a crucial role in the formation of covalent bonds. Imagine these electrons as the glue that binds the atoms together, forging a connection that's more than just physical. This phenomenon exemplifies the power of nature's forces. But our journey doesn't end here. We have more intriguing examples to explore. Hello again, bright minds. Let's take a closer inspection of the formation of a hydrogen molecule, shall we? In this scenario, we have two hydrogen atoms, each harboring a lone electron residing in its 1s orbital. Now, as these atoms approach each other, their orbitals begin to overlap. This overlap creates a region of heightened electron density between the nuclei. What's truly fascinating is that this electron density is a result of electron sharing, where the electrons from both atoms begin to dance in this shared space. It's as if they're participating in a molecular waltz. And remember, it's this synchronized dance that ultimately gives rise to a covalent bond, binding the atoms together. So, let's applaud the tiny dancers of the atomic world for their role in molecular creation. Next up, we'll venture into another captivating example. Fantastic job, inquisitive minds! As we journey through the world of molecular formation, we come to a profound understanding of nature's bond. Picture this. Two atoms, each with its own electron, coming together and creating a symphony of electron interaction. The orbitals overlap, and as they do, their electrons are drawn towards each other like old friends reuniting after a long time. This electron attraction, this camaraderie, results in the creation of covalent bonds. It's as if these atoms are shaking hands and saying, "Let's stick together and create something amazing." This unity and stability achieved through covalent bonds are what allow molecules to exist in our world. We've laid the foundation of our exploration. Now, let's build upon it as we unravel more mysteries of molecular chemistry. Hello, eager learners. Let's witness the valence bond theory in action with a step-by-step exploration of H2 formation. Remember, this theory helps us comprehend the intricate dance of electrons as atoms come together. Our journey begins with two hydrogen atoms, each with its single electron sitting in a 1s orbital. As these atoms approach each other, their orbitals start to overlap. This overlap creates a zone of heightened electron density between the nuclei. Imagine it as a realm where electrons decide to mingle and share their energetic secrets. This sharing of electrons leads to the establishment of a covalent bond between the atoms. Just like a handshake seals a friendship, this bond seals the atoms together, forming a hydrogen molecule. Our understanding of molecular chemistry keeps expanding, so let's press forward and explore more captivating examples. Welcome back, dear students. Today, we're delving into the intriguing world of covalent bonding and the concept of orbital overlap. This concept is vital in understanding how atoms come together to form molecules. Take the example of hydrogen-chlorine, where the chlorine atom possesses an electron configuration of 3 neon 4 sulfur 223 Pa(F)5. In this molecule, the valence orbitals of chlorine are almost full, except for one 3 Pa(F) orbital, which contains a single electron. Now, here comes the exciting part. This lone 3 Pa(F) electron pairs up with the single 1s electron from hydrogen. This pairing results in the formation of a covalent bond that holds the hydrochlorine molecule together. Remarkably, the other two chlorine 3 Pa(F) orbitals, which each have a pair of electrons, don't participate in the bonding process with hydrogen. Similarly, the covalent bond in chlorine 2 can also be understood through the overlap of the singly occupied 3 Pa(F) orbital of one chlorine atom with the singly occupied 3 Pa(F) orbital of another. This concept of orbital overlap, my dear students, is a cornerstone in comprehending the chemical interactions that shape our world. As we explore further, remember that the structure of molecules is intricately tied to the arrangement of their orbitals. Let's continue our journey into the fascinating realm of molecular bonding. As the hydrogen atoms come closer, their one's orbitals start to overlap. This overlap leads to an increase in electron density between the nuclei. This change in electron distribution results in a fascinating outcome. The potential energy of the system actually decreases. This signifies that the bond between the atoms is growing stronger. Null. And there you have it, our journey through the world of covalent bonds and potential energy changes. We've explored how the distance between nuclei affects the stability of a bond, and how electron overlap results in a stronger bond formation. Always remember, the energy change during this process provides us with valuable insights into the strength of the bond. With this understanding, we're equipped to delve even further into the intricate nature of chemical interactions. Keep up the great work, and let's continue our exploration of the wonders of chemistry. Hello, students. Today's topic brings us to the intriguing realm of potential energy within molecular systems. Imagine a two-atom system, like the example we're discussing. As depicted in Figure 9.13, the potential energy of this system experiences fluctuations based on the distance between the two hydrogen nuclei. Particularly, the energy sharply increases when the distance falls below 74 pm. Now, what's causing this rise in potential energy? It's primarily due to a force we're all familiar with: electrostatic repulsion. When the nuclei get too close, this repulsion becomes significant. At the minimum point of the potential energy curve, precisely at 74 pm in this case, we find the bond length of the molecule. This distance also corresponds to the bond's strength, as the potential energy at this minimum represents the energy needed to break the bond. It's a delicate balance of attractive forces between unlike charges, electrons and nuclei, and repulsive forces between like charges, electron-electron and nucleus-nucleus. Now, let's delve deeper into this fascinating world. Welcome back, curious minds. Our journey into molecular dynamics continues with a focus on electrostatic repulsion and its role in bonding. Think of it as a powerful driving force that influences how atoms interact. As the internuclear distance decreases, the strength of this repulsion becomes more pronounced. This phenomenon shapes the molecular landscape, leading to intriguing consequences for bonding. We're talking about a delicate equilibrium between forces: the attractive pull between electrons and nuclei, and the repulsive push between similar charges. It's this fine balance that determines the structure and stability of molecules. So, the next time you observe a molecule, remember that behind its arrangement lies a dance of charges and forces. Hello again, inquisitive learners. Let's delve deeper into the concepts we've been exploring. Bond length, a crucial factor in molecular architecture. It's the specific distance between two nuclei where the potential energy reaches its minimum value, as we've seen. This minimum potential energy signifies the strength of the bond. The closer the nuclei, the stronger the repulsion, and the higher the potential energy. But remember, it's not just about energy, it's about stability and structure. Different molecules have different bond lengths, and these lengths play a significant role in determining how molecules behave and interact. So, think of bond length as a sort of Goldilocks zone for atoms, where they find just the right balance between attraction and repulsion. Greetings, knowledge seekers. Our exploration of molecular bonds brings us to some fascinating insights. We've learned how the dance between attraction and repulsion shapes bond lengths and strengths. But what orchestrates this dance? Electrons, of course. They're the key players in mediating interactions between atoms, leading to various bonding types: covalent, ionic, and metallic. Each type presents a unique interplay between forces, and understanding these bonds is essential across scientific disciplines. From designing new materials to comprehending biochemical reactions, the world of molecular bonding holds the secrets to countless natural phenomena. So, keep your curiosity ignited as we unravel the mysteries of molecular interactions. Welcome back, students. In our last session, we delved into energy production through chemical reactions. Today, we're shifting gears and exploring the intriguing concept of hybridization across various fields. First up, let's talk about hybrid cars. Just like a hybrid car seamlessly switches between electricity and petrol as energy sources, our next example takes us to the realm of biology. In biology, a hybrid is an entity that combines traits from two different species, resulting in unique characteristics. A classic example is a mule, which inherits the strength of a donkey and the size of a horse. Now, let's venture into the realm of chemistry, where the term hybrid orbitals comes into play. Much like how a hybrid car blends two energy sources, hybrid orbitals in chemistry combine features of contributing orbitals. This blending results in orbitals that possess some of the shape and size characteristics of their parent orbitals. Are you ready to explore the fascinating world of hybridization across these diverse fields? Great to see your enthusiasm, class. Today, we're digging deeper into the concept of hybridization. Let's start with hybrid cars. These innovative vehicles combine two energy sources, electricity and petrol, creating an efficient and eco-friendly mode of transportation. The fascinating thing is that these energy sources remain separate and distinct. The car's computer system intelligently decides when to use each source based on factors like speed and load. This not only results in improved fuel consumption but also reduces harmful emissions. As we explore this topic, think about the parallels between the distinct energy sources in hybrid cars and the hybridization we encounter in other fields. Brilliant minds, let's continue our journey through hybridization. In the realm of biology, hybrids are truly remarkable. Imagine traits from two different species coming together to form an entity with unique characteristics. One famous example is the mule, which is a cross between a donkey and a horse. The mule inherits the strength from the donkey and the smaller size from the horse. It's astonishing how the combination of genetic material from two distinct species can give rise to such extraordinary offspring. Now, let's transition our focus to the world of chemistry, where a different type of hybridization awaits. Fantastic, my curious learners! Our exploration of hybridization continues, now leading us into the realm of chemistry. Here, we encounter the captivating concept of hybrid orbitals. Just like how hybrid cars and biological hybrids blend characteristics, hybrid orbitals combine traits of contributing orbitals. This blending gives rise to orbitals with properties that are intermediate between the original orbitals. These hybrid orbitals play a crucial role in understanding molecular shapes, as they help us explain the arrangement of atoms within molecules. As we journey deeper into the intricacies of hybrid orbitals, remember that this concept showcases the interconnectedness of various scientific disciplines. You're doing exceptionally well, my eager learners. Our exploration of hybridization brings us to a point of reflection. Hybridization isn't just a concept, it's a bridge that connects different branches of science. From hybrid cars blending energy sources to biological hybrids combining species traits. And finally, to hybrid orbitals uniting characteristics in chemistry. We see a common theme of unity and diversity. This interconnectedness between fields enhances our problem-solving abilities and fuels innovation. As you continue your academic journey, remember that understanding hybridization opens doors to cross-disciplinary applications and a deeper comprehension of the world around us. Marvelous work, dear students. As we conclude our session on hybridization, let's recap our exciting journey. We started with the world of hybrid cars, where two energy sources seamlessly blend. Then, we explored the realm of biology, where hybrids combine traits from different species, resulting in unique attributes. Lastly, we delved into the world of chemistry, unraveling the mystery of hybrid orbitals and their role in shaping molecular geometry. Throughout our exploration, we've discovered the beauty of unity and diversity, how different fields of science can come together to create something extraordinary. Remember, this interconnectedness is a testament to the power of cross-disciplinary learning. As you move forward, keep this concept in mind, and let it inspire your curiosity and innovation in all your academic pursuits. Welcome back, dear students. In this section, we're delving into a crucial aspect of understanding molecules, hybridization. By the end of this part, you'll have the skills to determine the hybridization of atoms within molecules based on the structures we observe. But why is this important, you ask? Well, the hybridization of atoms significantly influences a molecule's geometry and bonding properties. Being able to relate hybridization to molecular structures allows us to predict various molecular characteristics. Now, let's explore how we can achieve this feat. We'll learn about methods for observing molecular structures, and trust me, this knowledge will be a key tool in your chemistry arsenal. Ready? Let's dive in. Hello, brilliant minds. Today, we're unwrapping the key concepts behind hybridization. Think of hybridization as a dance of atomic orbitals. Atoms in a molecule mix their native orbitals to create new hybrid orbitals. These hybrid orbitals are essential for bonding, shaping the molecule's geometry, and determining its properties. By altering the arrangement of electrons, hybridization leads to the formation of strong, stable bonds between atoms. And guess what? The type of hybridization directly influences the molecular geometry, which in turn impacts its physical and chemical traits. So, as we progress, keep in mind how these hybrid orbitals contribute to the mesmerizing world of molecular structures. Greetings, curious minds. Today, we're uncovering the methods that allow us to observe the intricate dance of atoms within molecules. Imagine having special glasses that let you see atoms connecting and forming bonds. Well, we don't have magical glasses, but we do have incredible techniques like spectroscopy and imaging methods. These methods enable us to peek into molecular arrangements and identify hybridization patterns. We scrutinize bond lengths and angles, dissecting the clues they provide about hybrid orbitals. It's like being a molecular detective, uncovering the secrets of atoms in their bonding tango. So, let's explore these techniques and refine our skills in deciphering molecular mysteries. Welcome back, inquisitive scholars. Now that we've equipped ourselves with the art of observing hybridization, let's move on to its practical applications. Our newfound expertise allows us to predict various molecular properties. By understanding hybridization, we can unravel the secrets behind a molecule's reactivity, polarity, and even its biological functions. Imagine predicting the behavior of molecules in chemical reactions, or understanding why certain molecules have unique properties. We'll journey through real-world examples, exploring how hybridization influences molecules like methane, ethene, and more complex compounds. So, buckle up, because we're about to embark on an exciting journey of applying hybridization knowledge. Null. Great questions, class. To understand the tetrahedral arrangement in methane, we need to journey into the world of atomic orbitals and covalent bonding. Covalent bonds are formed by the overlapping of atomic orbitals. Now, let's focus on carbon in methane. The US and UP orbitals of carbon overlap with hydrogen's 1s orbital. Here's where hybridization theory comes in. The carbon's US and UP orbitals undergo sp3 hybridization, leading to the formation of 4 equivalent hybrid orbitals. These hybrid orbitals align themselves tetrahedrally, perfectly accommodating the arrangement of the hydrogen atoms. This explains how the seemingly non-directed US and UP orbitals manage to create a tetrahedral arrangement. Fascinating, isn't it? Hybrid orbitals are truly remarkable. They combine the characteristics of their parent orbitals and adapt to the needs of bonding. In the case of methane, sp3 hybrid orbitals emerge from the combination of the 2s and 2p orbitals. The beauty lies in their orientation. These hybrid orbitals are specifically directed toward the apices of the tetrahedron. This directedness allows carbon to form strong sigma bonds with the surrounding hydrogen atoms, resulting in the tetrahedral molecular geometry that we observe in methane. This incredible molecular arrangement is a testament to the versatility and adaptability of atomic orbitals. Brilliant work, students! We've successfully bridged the gap between the VSEPR model and atomic orbitals. The VSEPR model predicts molecular geometry, while hybridization theory explains the underlying bonding. In the case of methane, hybridization aligns perfectly with the VSEPR predicted tetrahedral arrangement. This synergy extends beyond methane to various molecular geometries and compounds. As we continue exploring the wonders of chemistry, remember that these theories and concepts build the foundation for our understanding of the intricate world of molecules and their shapes. And there you have it, dear students. Our exploration into the VSEPR model, atomic orbitals, and molecular shapes has shed light on the remarkable mechanisms governing the arrangement of atoms. Understanding these concepts isn't just about theory, it's about comprehending the very nature of chemical properties and reactions. The complexity of the molecular world is an ongoing source of inspiration for researchers around the globe. As we conclude today's lesson, remember that the journey of discovery in the realm of chemistry has only just begun. So, get ready for more captivating journeys ahead, where we unveil the mysteries of the molecular universe. Until next time. Good day, students. Today, we're embarking on an exciting journey into the realm of atomic and hybrid orbitals. Let's start by recapping what atomic orbitals are. These are mathematical functions derived from the quantum mechanical model of atomic structure. They help us understand the arrangement of electrons within an atom. Now, to delve into molecular geometries, we often make use of a fascinating concept: hybrid orbitals. These are new orbitals formed by mixing atomic orbitals, and they play a crucial role in determining the shape of molecules. It's important to note that hybrid orbitals have shapes distinct from the original atomic orbitals. The process of mixing these atomic orbitals is known as hybridization, a mathematical operation that results in hybrid orbitals. Remember, the total number of atomic orbitals on an atom stays the same during hybridization, and this determines the number of hybrid orbitals formed. So, let's dive deeper into the world of atomic and hybrid orbitals. Welcome back, students. Now that we've laid the groundwork, let's explore hybridization and its role in predicting molecular shapes. Hybrid orbitals are our key tools for understanding these shapes. Hybridization takes place when atomic orbitals of different energy levels come together. The outcome is a set of hybrid orbitals with distinct properties. The number and types of hybrid orbitals formed depend on the specific atomic orbitals that undergo hybridization. For instance, let's take sp³ hybridization as an example. This involves mixing one s orbital and three p orbitals to yield four sp³ hybrid orbitals. These hybrid orbitals pave the way for explaining the tetrahedral geometry of molecules like methane, Ch. So, you can imagine hybridization as the artist behind the canvas of molecular shapes. It's truly fascinating how the atomic building blocks come together to create these intricate forms. Let's move on to the next chapter of our exploration. Hello again, eager minds. Let's unveil the remarkable applications of hybridization in understanding the properties of molecules. Hybridization influences essential factors such as bond angles, bond strengths, and overall reactivity. Think of it as a master conductor orchestrating the symphony of molecular characteristics. Consider the case of sp² hybridization in ethene, C2H4. This unique hybridization leads to the formation of a double bond and results in a planar structure. This example highlights how hybridization plays a vital role in determining molecular properties. Moreover, the diversity of hybridization types contributes to the vast array of organic compounds we encounter in everyday life. From the complexity of biological molecules to the simplicity of hydrocarbons, hybridization gives us insights into the stability and behavior of these compounds. Isn't chemistry a fascinating world of its own? Let's continue exploring. Welcome back, inquisitive minds. Let's take a moment to recap our journey into the captivating world of atomic and hybrid orbitals. We began by understanding that atomic orbitals are mathematical functions that guide us through the arrangement of electrons within an atom. Then, we delved into the captivating concept of hybrid orbitals. These hybrid orbitals, formed through the mathematical operation of hybridization, provide us with valuable insights into predicting molecular shapes and understanding the properties of compounds. Remember, hybridization affects bond angles, strengths, and reactivity, ultimately shaping the behavior of molecules. The diversity of hybridization types adds to the richness of organic chemistry, where we encounter a wide range of compounds. As we conclude our journey today, remember that the study of hybridization opens doors to unraveling the intricacies of complex molecular structures. Keep exploring, keep questioning, and keep nurturing your curiosity. Until next time. Null. Hello, dear students. Today, we're venturing into the world of atomic bonding and electron promotion. Our focus shifts to the beryllium atom and its intriguing bonding capabilities. You see, in its ground state, beryllium faces a challenge. Due to the absence of unpaired electrons, it struggles to bond with fluorine atoms. But fear not, for science always finds a way. Imagine this. By promoting one of the 2s electrons to a 2p orbital, the beryllium atom gains newfound potential. This opens up a whole new avenue for bonding. Now, instead of being limited by its ground state, beryllium can form not 1, but 2 bonds. Visualize this arrangement as 1's 2's 2p. Isn't it amazing how a simple rearrangement of electrons can lead to such bonding possibilities? Keep this concept in mind as we journey deeper into the intricate realm of atomic interactions. Hello, students. Welcome to our second topic, where we'll delve into the intriguing world of bond formation in beryllium fluoride, BEF. Now, we've learned that the beryllium atom has 2 unpaired electrons, which means it has the potential to form bonds with other atoms. In this case, beryllium forms polar covalent bonds with fluorine atoms. What's fascinating is that these bonds aren't identical. Why? Well, it's due to the way beryllium's electron orbitals come into play. One of the bonds is formed using a 2s orbital, while the other employs a 2p orbital. This orbital distinction gives rise to the asymmetry in the bonds. But, how does all of this explain the structure of BEF? Let's move on to the next topic to unravel this mystery. Great to have you back, students. We're about to unlock the secret behind the structure of beryllium fluoride, BEF. Imagine, we have beryllium and 2 fluorine atoms. The arrangement of these atoms gives rise to a unique structure. Brace yourselves, BEF has a linear molecular geometry. This means that the atoms are aligned in a straight line. You might wonder, how does this geometry connect with what we learned earlier? Well, it's all about those two polar covalent bonds we discussed. These bonds, formed between beryllium and fluorine, contribute to the linear structure. The arrangement of atoms and the nature of these bonds collectively shape the overall structure of BeF. Ready to explore more? Let's proceed. Hello again, curious minds. In this topic, we're going to dive deeper into the electron arrangement within beryllium fluoride, BeF. Remember the electron configuration of beryllium? It plays a significant role in the formation of bonds. When beryllium bonds with fluorine, there's a transfer of electron density. This transfer leads to partial positive and negative charges on the atoms. These charges create what we call a dipole moment, which essentially represents the separation of charges within the molecule. The polarity resulting from this charge separation influences the molecule's behavior and interactions with other molecules. So, the distinct electron arrangement in BeF contributes to its overall properties. Fascinating, isn't it? Let's keep our exploration going. Hello, students. Today's lesson continues with an exploration of a fascinating concept called hybridization. We're going to take a closer look at how we can manipulate orbitals to generate new ones. Imagine combining a 2s orbital and a 2p orbital. This combination results in the creation of two new orbitals, each with a unique structure. Unlike the equal-sized lobes of p orbitals, these new orbitals have one significantly larger lobe and one smaller lobe. It's important to note that these two new orbitals maintain the same shape, but they point in opposite directions. These specialized orbitals are known as hybrid orbitals, and in this case, because we've combined an s and a p orbital, they are called sp hybrid orbitals. This hybridization process is responsible for creating a linear arrangement of electron domains, which has important implications for molecular geometry. So, let's delve deeper into the intricacies of hybridization and its role in shaping molecules. Welcome back, everyone. As we delve further into the world of hybridization, let's connect the dots between molecular arrangements and electron domains. When we talk about the linear arrangement of electron domains, we're essentially discussing how the electron clouds around atoms are positioned. This arrangement plays a vital role in molecular geometry. Now, remember our sp hybrid orbitals? They come into play here. Because of their unique properties, molecules that undergo sp hybridization exhibit a linear molecular shape. This is an excellent example of how understanding hybridization and electron domain geometry can help us predict the shapes of molecules. So, let's keep our focus sharp as we journey into more examples and dive deeper into the impact of hybridization on molecular structures. Great to see you all engaged today. Our exploration of hybridization isn't just about theory. It has practical implications too. Understanding hybridization is like unlocking a treasure trove of insights into the properties and behaviors of molecules. Hybridization significantly affects molecular polarity and reactivity. Take molecules with sp hybridization, for instance. They have distinct characteristics that make them polar or reactive in specific ways. Consider the compound examples we've got, and think about how these principles apply in real-world scenarios. From materials science to pharmaceuticals, the applications of sp hybridization span various industries. As we venture forward, be ready to connect the dots between theory and its practical applications. Hello again, eager learners. Let's take a moment to reflect on our journey so far. We've uncovered the concept of hybridization and the birth of sp hybrid orbitals by mixing 2s and 2p orbitals. This manipulation has a direct link to molecular geometry, which shapes the way molecules interact and behave. By understanding hybridization, we gain a powerful tool to predict the shapes of molecules, which has far-reaching implications across chemistry. Our applications of sp hybridization showcase its relevance in industries beyond the classroom. As we wrap up this part of our exploration, I want you all to remember that chemistry is a gateway to understanding the world on a molecular level. We're on the verge of diving into even more exciting aspects of this fascinating subject. So, Get ready to unlock more secrets of the chemical world in our upcoming lessons. Hello, dear students. In today's lesson, we're delving into the world of molecular structures and bonding. Let's start by focusing on the fascinating case of BEF. Picture this. The electrons residing in the sp hybrid orbitals of beryllium have the ability to form bonds with two fluorine atoms. The intriguing aspect here is that the sp hybrid orbitals are equivalent but point in opposite directions. As a result, BEF exhibits a linear geometry. This geometry is a result of those two identical bonds formed between the sp hybrid orbitals of beryllium and the fluorine atoms. Now, remember, we've utilized one of the two p orbitals in the process of hybridization, leaving behind two unhybridized and vacant 2p atomic orbitals of beryllium. It's also important to note that each fluorine atom holds two additional valence p atomic orbitals, each containing a non-bonding electron pair. While these atomic orbitals aren't shown in figure 9.15, their presence adds complexity to the overall picture. Alright, let's move on to the next topic and explore more intricacies. Good day, students. Today, we're delving into the intriguing concept of hybrid orbitals and their formation. Imagine combining atomic orbitals to create new structures known as hybrid orbitals. What's fascinating is that the number of hybrid orbitals formed is identical to the number of atomic orbitals mixed. These hybrid orbitals are not only equal in number but also share the same characteristics, even though they point in different directions. To illustrate, let's consider the combination of a 2s and a 2p atomic orbital. This results in the generation of two equivalent sp hybrid orbitals that extend in opposite directions. Take a look at figure 9.14 for a clearer visual. Remember, this phenomenon isn't limited to just sp hybridization. We can also achieve distinct geometries like sp2 and sp3 hybridizations. These hybridization processes play a crucial role in understanding molecular shapes and bonding. So, buckle up as we venture deeper into the world of hybrid orbitals and their implications. Welcome back, students. Today, we're going to delve into a specific type of hybridization known as sp2 hybridization. To achieve sp2 hybridization, we mix one 2s orbital with two 2p orbitals. This combination gives rise to three equivalent sp2 hybrid orbitals. These hybrid orbitals arrange themselves in a trigonal planar geometry with bond angles of 120 degrees. This geometric arrangement leads to the creation of some interesting molecules. Take, for instance, boron trichloride, BCl3, and ethene, CuH4. In both these cases, sp2 hybridization plays a pivotal role in determining their molecular structures. As you can see from the molecular models in our image, the concept of sp2 hybridization is not only fascinating but also essential in explaining the shapes and properties of various compounds. So, let's keep exploring. Hello again, students. Now, let's journey into the realm of sp3 hybridization. This type of hybridization involves mixing one 2s orbital with three 2p orbitals, resulting in the creation of four equivalent sp3 hybrid orbitals. These hybrid orbitals arrange themselves in a tetrahedral geometry, where the bond angles are approximately 109.5 degrees. The significance of sp3 hybridization becomes evident when we observe molecules like methane, CH4, and ammonia, NH3. These molecules adopt distinct shapes due to the arrangement of their sp3 hybrid orbitals. As shown in our molecular models, methane and ammonia both showcase tetrahedral geometries, which are a direct result of sp3 hybridization. Isn't it remarkable how the combination of atomic orbitals leads to such diverse molecular structures? Our exploration of hybrid orbitals continues, shedding light on the intricacies of chemical bonding and molecular geometry. Stay curious and engaged, as we uncover more. Welcome, students, to an exciting exploration of hybridization and molecular geometry. Today, we're delving into the fascinating world of boron trifluoride. where atomic orbitals come together in a unique way. In boron trifluoride, the mixing of two U atomic orbitals and two of the UP atomic orbitals results in something extraordinary: three equivalent SPU hybrid orbitals. Picture this. These SPU hybrid orbitals are like a blend of the original orbitals, allowing for an efficient arrangement. These three SPU hybrid orbitals lie in the same plane, each separated by 1–2 degrees from the others. This specific arrangement is crucial as it enables the formation of bonds. In the case of boron trifluoride, these SPU hybrid orbitals combine with fluorine atoms, leading to the distinctive trigonal planar molecular geometry that characterizes boron trifluoride. Now, remember that amidst all this hybridization, an unfilled UP atomic orbital remains unchanged. It's oriented perpendicular to the plane defined by the three SPU hybrid orbitals, with one lobe above and one below the plane. Keep this in mind as we move forward, especially when we dive into double bonds in our upcoming discussions. Exciting times ahead as we unravel the intricacies of molecular structures. Welcome back, dear students. Today, we're delving into the intriguing concept of hybridization, which plays a crucial role in understanding the bonding within molecules containing non-bonding pairs of electrons. Let's take a specific example to better grasp this concept. In the water molecule, H2O, the electron domain geometry around the central oxygen atom is roughly tetrahedral, as depicted in Figure 9.18. Now, here's where hybridization comes into play. We can envision the four electron pairs around the oxygen atom occupying sp3 hybrid orbitals. Among these, two hybrid orbitals contain non-bonding pairs of electrons, while the other two form bonds with the hydrogen atoms, giving rise to the unique structure of H2O. This concept allows us to better comprehend the intricate arrangements of electrons within molecules. Let's move forward and explore more captivating examples. Good day, students. Today's topic takes us beyond our previous discussions on hybridization and introduces a fascinating concept known as hypervalent molecules. Up until now, we've primarily focused on period 2 elements like carbon, nitrogen, and oxygen when discussing hybridization. However, when we move to elements in period 3 and beyond, things get a bit more intricate. These elements often form compounds where they have more than an octet of electrons around the central atom. Imagine that more electrons than the usual 8. One way to visualize this is through examples like phosphorus pentachloride, SF6, and BRF5, where the VSEPR model helps predict their geometries quite well. Now, let's explore whether we can apply hybrid orbitals to understand the bonding in these unique molecules. Welcome to our second topic, dear students. Today, we delve into a critical question. Can we use hybrid orbitals to explain the bonding in hypervalent molecules? The answer, quite surprisingly, is a firm no. While hybrid orbitals have proven immensely useful for explaining the bonding in simpler compounds, they fall short when it comes to the complexity of hypervalent molecules. But why is this the case? Let's explore the reasons behind this limitation. Topic 3. Here we are. Now, let's uncover the reasons that make hybrid orbitals incompatible with hypervalent molecules. First, we must acknowledge that hypervalent molecules have a unique feature: extended octets. This means they have more than 8 electrons around the central atom, which is different from what we see in our earlier discussions. Hybrid orbitals are particularly well suited for explaining localized bonding, where electrons are shared between specific atoms. However, in hypervalent compounds, the bonding is more delocalized, meaning electrons are spread out over larger regions. This complexity goes beyond what hybrid orbitals can effectively account for. Additionally, the involvement of d orbitals in hypervalent elements further complicates the situation. Let's take a moment to appreciate the intricate dance of electrons in these molecules. We're on Topic 4 now, and it's time to explore some alternatives. As we've established that hybrid orbitals aren't the go-to tool for understanding hypervalent molecules, what can we turn to? Enter valence bond theory and molecular orbital theory. These are two intriguing alternatives that offer better explanations for the unique bonding in hypervalent compounds. Valence bond theory emphasizes the overlap of atomic orbitals, shedding light on the sharing of electrons between specific atoms. On the other hand, molecular orbital theory takes a broader approach, considering the formation of molecular orbitals through the combination of atomic orbitals. Both these theories give us more insight into the intricacies of hypervalent bonding. Now, let's move on to our final thoughts. Dear students, as we wrap up our exploration of hypervalent molecules, remember that chemistry constantly presents us with challenges and mysteries. While hybrid orbitals might not be our key to understanding these complex compounds, we've learned about alternatives like valence bond theory and molecular orbital theory. These theories open doors to a deeper understanding of the intricacies of chemical bonding. The world of chemistry is vast, and there's always more to explore and discover beyond our classroom discussions. So, I encourage each of you to continue your journey into the realm of science, curiosity, and discovery. With that, we conclude today's lesson. Until next time. Hello again, dear students. Today, we're delving into the fascinating world of molecular bonding and extending our understanding of the valence bond model. As we know, the valence bond model is a powerful tool to explain the bonding in compounds of period 2 elements. This model helps us understand the sharing of electrons between atoms, forming bonds. Now, let's think bigger. When we look at compounds of period 3 elements, we can still utilize the valence bond model as long as we follow a key principle, the octet rule. This rule states that atoms tend to gain, lose, or share electrons in order to achieve a stable configuration with 8 electrons in their valence shell. This is where our model comes into play, but there's a twist. In compounds like PF3 or hydrogen selenide, where the central atom has no more than an octet of electrons, we can discuss their bonding in terms of hybridized s and p orbitals. These hybrid orbitals are a fascinating result of atomic orbital mixing, and they enable us to better understand how these elements form bonds and achieve stability. So, as we journey through this intricate topic, remember, we're expanding our understanding while sticking to the fundamental principles we've learned. Onward to more knowledge. Hello, students. Today, we're going to delve into an intriguing concept related to molecular structures, particularly when compounds decide to break the octet rule. As we know, many compounds prefer having 8 electrons in their valence shell, but there are exceptions. Compounds like SF6 challenge this rule and go beyond 8 electrons. How do they do this? By incorporating valence shell d orbitals alongside the more common s and p orbitals. Let's take SF6, for instance. In this molecule, sulfur uses its 3s, 3p, and even its 3d orbitals to form hybrid orbitals. These hybrid orbitals then combine with the orbitals of 6 fluorine atoms, resulting in the unique structure you see on the screen. This deviation from the octet rule allows these compounds to accommodate more than 8 electrons in their valence shells, opening up a world of possibilities for molecular diversity. Now, let's continue our exploration of fascinating chemical phenomena. Good day, students. Today, we're going to delve into the intriguing world of molecular bonding, particularly focusing on the bonding in the sulfur hexafluoride molecule. Picture this. We have sulfur, a central atom, surrounded by 6 fluorine atoms. Now, to understand the bonding, imagine mixing 2 sulfur 3d orbitals with the 3 3s and 3 3p orbitals. This would give us a total of 6 hybrid orbitals. But hold on. Here's where it gets fascinating. The sulfur 3d orbitals are higher in energy compared to the 3s and 3p orbitals. This means that it takes more energy to create these hybrid orbitals than the energy gained from forming bonds with the 6 fluorine atoms. It's like an energy balancing act. Alright, students, let's take a closer look. The sulfur 3d orbitals are higher up on the energy scale compared to the 3s and 3p orbitals. This means that the energy required to create those hybrid orbitals is actually more than what we gain from forming bonds with the 6 fluorine atoms. Interestingly, theoretical calculations show that these sulfur 3d orbitals don't play a major role in bonding with the fluorine atoms. It's like they're hanging out in the background while other orbitals take the spotlight. Now, students, here's where things get a bit more complex. The bonding in AF6 requires a deeper, more detailed model than what we cover in general chemistry. We're talking about a level of intricacy that goes beyond what we typically explore. But fear not. There's a model that comes to our rescue, and that's the VACEPR model. This nifty model helps us understand the geometrical properties of molecules like AF6 based on the electrostatic repulsions between their atoms. It's like using a puzzle piece to predict the overall shape. Let's take a moment to appreciate the VSEPR model, students. VSEPR stands for valence shell electron pair repulsion. This model is our key to unlocking the mystery of molecular geometries. It works by considering the repulsions between electron pairs in the valence shell of an atom. This concept helps us predict the shapes that molecules like SF6 will adopt. And guess what? The VSEPR model has a strong track record, even when it comes to those complex hypervalent molecules. It's like having a virtual geometry guru. As we wrap up our exploration, students, remember this. The bonding in SF is a dance of intricate orbital interactions. The sulfur 3d orbitals might not be the stars of the show, but they play a supporting role. And when it comes to understanding how these molecules arrange themselves in space, the VSEPR model is our trusty guide. It helps us predict geometries by considering the repulsions between electron pairs. So, next time you encounter a molecule like SF, you'll know that there's more than meets the eye, and the VSEPR model is here to shed light on its secrets. Hello, students. Today, we're delving into the intriguing world of scientific models and their role in understanding the complexities of molecules. Our journey begins with the recognition that scientific models are not reality itself, but rather are attempts to capture specific aspects of reality that we can measure. Think of them as tools we use to describe properties like bond distances, bond energies, and molecular geometries. These models help us make sense of the chemical world around us. Let's move forward to explore the fascinating concept of hybrid orbitals. Now, let's focus on a specific model that has revolutionized our understanding of bonding and molecular geometry, the hybrid orbital model. This model is like a puzzle solver for complex molecules. It's incredibly helpful, especially when dealing with elements from period 2 of the periodic table. By using hybrid orbitals, we can unlock the secrets of molecular structure and bond angles, allowing us to predict how atoms come together to form molecules. This knowledge is a cornerstone of modern organic chemistry discussions. However, like any tool, the hybrid orbital model has its boundaries. It excels in many cases, but there are instances where its effectiveness diminishes. Consider molecules, like SF6. This compound challenges the hybrid orbital model's abilities due to its unique complexity. The model struggles to fully explain the molecular geometry and bonding in such cases where valence shells become highly expanded. It's important to remember that scientific models, while powerful, are not all-encompassing. They have their strengths and limitations. As we conclude our exploration of the hybrid orbital model, let's keep in mind that science is a dynamic field. Our understanding evolves over time, and so do our models. The limitations we encounter today might lead us to new breakthroughs tomorrow. Quantum mechanics, for instance, provides deeper insights into the behavior of molecules at the atomic level. Yet, models like hybrid orbitals remain essential tools for introducing these concepts and understanding the basics of molecular bonding. Our journey through the world of models and molecules continues to shape our understanding of the chemical universe. Before we conclude, let's reflect on the broader context. Chemistry is a captivating science, full of intricate phenomena and diverse molecules. Models are our guides on this journey, but they might not capture every nuance. Embrace the complexity that comes with the territory. Our journey in chemistry is one of continual exploration and learning. Each discovery, each limitation, takes us closer to unraveling the mysteries of the chemical world. So, keep your curiosity alive and your minds open as we navigate the fascinating realm of science.